Ceramic tiles look ordinary, but their life begins as raw earth and ends as a surface as hard as stone.
In the next half hour, we follow one tile from clay and kaolin to a finished bathroom floor.
No shortcuts, no myths, just the real industrial steps that make a tile flat, strong, and waterproof.
You will see where the raw minerals come from, how they become powder, how patterns are printed, and how fire locks everything in place.
Along the way, we'll point out the tiny mistakes that create big defects: warping, pinholes, cracks, and color shifts.
A ceramic tile is a layered composite, not just a slab of baked mud. Inside is the body, a dense ceramic made from clays and mineral additives.
On top is the glaze, a thin glass layer that melts in the kiln and bonds to the body. The body is built for strength and stability, while the glaze is built for beauty and protection.
Glaze can be glossy like glass, soft matte like stone, or textured for grip in wet areas.
Some tiles are unglazed, but most bathroom and kitchen tiles rely on glaze for stain resistance. In retail, people often compare ceramic and porcelain.
Porcelain usually uses a more refined body, is fired hotter, and ends up denser with lower water absorption.
But the factory logic is similar. Mix minerals, control particle size, shape the tile, dry it, coat it, and fire it on a curve.
A tile's performance is measured in plain, practical terms. Does it stay flat across its width, or does it bow after firing?
Does it absorb water, or does it resist moisture for decades? Does the surface scratch easily, or does it survive sand?
Tiles are also judged by consistency, edge straightness, corner squareness, and how well patterns match from tile to tile. That consistency depends on tight process control, because ceramics do not forgive mistakes.
Once a tile is fired, you cannot bend it back, repaint it, or hide hidden cracks inside. So modern
The story starts at the quarry, where excavators cut into layered deposits of clay and kaolin.
Kaolin is prized because it is relatively pure and fires to a light color, which helps bright glazes stay clean and consistent.
Other clays add plasticity, meaning the mix can be shaped without cracking or tearing.
Some clays contain more iron and fire darker. These can be used in certain products, but they change the final color.
Factories also use fluxes such as feldspar or nepheline cyanide, which help the body partially melt during firing. That partial melt is not a flaw. It is the mechanism that densifies the tile and locks particles together. Silica, often in the form of quartz, helps control shrinkage and keep the fired tile dimensionally stable.
A modern tile body is a recipe, and each ingredient has a job: shapeability, strength.
But raw minerals are natural materials, and nature varies. One truckload of clay may have slightly different moisture, different grain size, or different chemistry than the last.
So the first rule of tile production is testing and consistency.
At receiving, East Asian male technicians take samples from multiple points in a shipment, then blend and test, rather than trusting a single scoop.
In the lab, they measure moisture content because water level affects grinding, spray drying, pressing, and drying.
They measure particle size distribution because packing and sintering depend on how fines and coarse particles fit together.
They measure chemistry, often using instruments like X-ray fluorescence, to track oxides that affect firing and glaze color.
They also screen for contaminants such as organics, salts, and iron that can create stains, bloating, or black specks.
Plasticity is tested too, because a body that is too short will crack, while a body that is too plastic can warp.
Some labs fire small test bars to see shrinkage and color at target temperatures before full production begins.
If the numbers drift, the recipe is adjusted. A little more feldspar for densification, a little more clay for strength, a little more silica for stability.
In many plants, raw materials are stored and aged so moisture equalizes before use.
This reduces sudden variations that would otherwise show up as density changes in pressed tiles.
Large operations blend clays from different pits, creating a stable average composition across the season. Suppliers are qualified, and raw materials are traced by lot numbers, so problems can be isolated quickly.
At the quarry, materials may be washed or screened to remove stones and organic debris. Some kaolin deposits are refined by washing to reduce iron, which would otherwise tint the fired body. Moisture control begins here. Covered stockpiles and lined storage prevent rainwater from changing consistency overnight.
Because clays can settle and segregate during transport, sampling is done at multiple depths and positions. A good plant builds a statistical picture of each supplier, tracking variation over weeks, not just one day.
That data helps them predict how the body will behave in the kiln and how the glaze color will read on top.
Raw clays often arrive as hard lumps, stones, and layered chunks. To make a uniform mix, the plant breaks everything down in stages.
First, crushers reduce large rocks into manageable pieces.
Then hammer mills or roll crushers break the material further so it can be measured and mixed evenly.
Dust collection is critical here. Fine mineral dust is not only messy, but also a serious respiratory hazard. After crushing, materials are stored in covered bays or silos to stabilize moisture and prevent contamination.
From storage, conveyor belts and wave feeders pull precise amounts of each ingredient. Those streams merge into blenders that
Blending is more than stirring. It is engineering how particles pack under pressure. A well-blended mix.
A poorly blended mix creates weak zones that become cracks or warped corners later. Plants also remove tramp materials, bits of wood, plastic, or stones, because they burn out or expand and create voids. In blended dry systems, operators also control the feed rate, so materials do not pulse in waves.
Pulsing creates alternating rich and lean zones of flux, which can show up later as size variation after firing.
Some plants install metal detectors and stone traps to protect mills and prevent catastrophic tool damage.
Many factories convert the dry blend into a slurry through wet milling.
Before milling, blungers or high shear mixers wet the powders quickly and break soft lumps.
Inside a rotating ball mill, water and the mineral mix tumble with hard grinding media for hours. The grinding media can be alumina or other ceramics, chosen to resist wear and avoid contamination.
As the mill turns, particles fracture and become finer, while water keeps everything flowing and prevents dust.
Operators don't guess when milling is done. They sample the slurry and test it.
They check viscosity, because a slurry that is too thick won't pump well and won't spray dry consistently.
They check density, because too much water wastes energy and changes granule structure. They check residue through sieves, because oversized grit can become a weak point in a tile.
Chemistry matters too. Deflocculants keep particles dispersed so the slurry stays fluid with less water.
Less water means less energy later, because the spray dryer has less to evaporate. Anti-foam agents prevent trapped air that could later cause bubbles in granules and glaze defects.
Some plants de-air the slip in vacuum tanks so pumping is smoother and spray drying is more consistent.
After milling, the slurry is screened, then sent through magnetic traps to remove iron particles from equipment wear. Even tiny metal specks can show up as dark freckles after firing, especially under light glazes.
Technicians watch pH and temperature because both affect stability and flow. Water systems are often closed-loop, filtering and recycling process water to reduce waste and keep chemistry consistent.
A stable slurry produces stable granules, and stable granules produce stable pressed tiles.
Inside the mill, time and speed are adjusted so the slurry reaches a target fineness without over-grinding.
Overgrinding can make the body shrink more, and it can increase the risk of warpage in large tiles.
Plants also control solids loading because thicker slurry saves energy but requires stable dispersal.
If dosage is too high, the slurry can become unstable and settle, creating inconsistent feed to the spray dryer.
A slurry is useful for grinding, but pressing requires a free-flowing powder.
To create that powder, the slurry enters a spray dryer, one of the tallest machines in a tile plant.
Pumps push the slurry to atomizing nozzles that break it into a cloud of fine droplets.
Hot air rushes through the tower, evaporating water in seconds.
Instruments. Each droplet becomes a small granule, often hollow and slightly porous, with a controlled surface moisture.
If granules are too wet, they stick in molds and cause density variation.
If they are too dry, they won't bond under pressure and can cause lamination cracks.
Factories measure powder moisture constantly and adjust inlet air temperature and feed rate to keep it within a tight band.
They monitor granule size distribution because a mix of sizes helps powder pack efficiently in the mold.
Operators watch cyclone collectors and filters that capture fine powder from exhaust air.
Recovered fines may be blended back carefully. Too many fines can change flow and pressing behavior. They also watch the temperature of exiting powder.
If it is too hot, granules can clump in silos. If too cool, moisture may be too high for stable pressing.
To keep flow smooth, silos use vibration or aeration, so powder does not bridge or form tunnels.
The finished powder moves to silos that feed the press line steadily, like flour feeding a bakery.
Spray drying also sets the internal structure of each granule. A good granule fractures and collapses under press pressure, filling voids and creating uniform density.
A bad granule resists compaction, leaving hidden pores that become weak points or cause differential shrinkage.
Powder flow is tested in small funnels and press trials, because silos and feeders can behave differently than lab cups.
Shaping usually happens by hydraulic pressing.
Granulated powder drops into a steel mold, and vibration helps it settle so density is even from corner to corner. Then the press closes with enormous force, compacting the powder into a rigid green tile. In a single cycle, the press controls fill weight, pressure curve, dwell time, and ejection speed. Those parameters matter because pressed powder behaves like a granular material, not like wet clay.
Air must escape as the powder compacts. If air is trapped, it forms planes of weakness.
Those weak planes can split during drying or expand in the kiln and create blisters. Molds are precision tools, and they wear.
Edges can become rounded, patterns can lose detail, and thickness can drift if tooling is not maintained.
For large format tiles, even small thickness variations can cause bending during firing, so presses are calibrated constantly. Some plants use multi-cavity molds to increase throughput, which makes uniform filling even more important. Press maintenance includes cleaning, lubrication, and checking punch flatness to avoid imprint marks.
Dust control is constant. Extraction hoods capture fine powder to keep molds clean and protect South Asian workers.
Some products use decorative surface granulates before pressing to create through-body speckled looks. After ejection, the green tile looks finished, but it is still fragile, like a dense chalk tablet.
Robots handle tiles by the edges,
place them on conveyors and avoid impacts that could start cracks.
Pressing creates not only shape, but also density distribution through the thickness.
If the top surface is denser than the bottom, tiles can curl during firing like a bimetal strip.
To prevent this, presses tune filling, vibration, and pressure ramps so the compact is uniform. Screen tiles may pass under edge rollers or light calibrators that remove burrs and improve stacking.
Plants continuously measure thickness and weight to catch drift before it becomes a kiln-wide problem.
Pressed tiles still contain moisture from the spray-dried powder. That moisture must leave before firing, or it will turn to steam and rupture the body. Drying sounds simple, but it is one of the main causes of warping if done carelessly.
If the surface dries and shrinks faster than the core, stress builds and the tile curls. So industrial dryers use multiple zones.
Early zones are warm and humid to move water gently from inside to the surface.
Later zones are hotter and drier to finish the job once the tile is more stable.
Airflow is engineered to be even across the width of the tile. Sensors track temperature and moisture so operators can adjust in real time.
Dryer belts and rollers must stay clean because debris can imprint the underside and create stress points.
Plants control tile exit temperature so glaze does not flash dry on contact and trap bubbles. After drying, tiles are flatter, lighter, and strong enough for glazing lines. Some products get light brushing or edge cleaning to remove dust and improve adhesion.
Dryers aim for a final moisture that is low enough for safe firing, but not so low that surfaces become dusty.
If the tile surface is dusty, glaze adhesion becomes unreliable and crawling risk increases.
Some lines use light misting or controlled humidity at the end of drying to stabilize surfaces before glazing.
Now the tile gains its final face. Most bathroom and kitchen tiles use glaze because
glaze is essentially glass in powdered form, silica plus fluxes plus additives that control melt behavior.
Pigments provide color, opacifiers provide whiteness, modifiers adjust gloss and surface tension.
Glaze is milled and mixed into a liquid suspension, so it can be applied evenly.
Rheology matters here. The way the glaze flows, levels, and holds on a vertical surface before firing.
If viscosity is wrong, glaze can sag, streak, or trap bubbles.
Many tiles first receive an engobe, an intermediate coating that improves bonding and masks the body color.
Engobe also smooths pores, so later glaze layers sit evenly and print colors stay consistent.
On the production line, tiles move under applicators that lay down layers at high speed.
Spray systems create even coats. Disc or bell applicators control thickness precisely. Roller coaters create a consistent film.
Curtain coaters can pour a continuous sheet of glaze, producing extremely uniform coverage.
Thickness is controlled in tenths of a millimeter because many glaze defects are thickness defects. Too thin and the surface looks dry and uneven.
Too thick and glaze can run in the kiln, pool at edges, or crawl away from contaminated spots. Factories monitor glaze density and solids content, topping up water and additives to keep the mix stable.
They filter glazes to remove clumps that could leave bumps or cause pinholes. After base layers, many factories add digital inkjet printing.
Unlike paper printing, ceramic printing uses inorganic inks designed to survive firing.
These inks rely on mineral pigments and metal oxides suspended in a carrier fluid.
Print heads deposit tiny droplets in multiple passes, building up images from layered color. Those passes build depth, shadows, highlights, and subtle variation that mimics stone, wood, or concrete. The printer must stay aligned with the moving tile. Cameras correct position so patterns register properly.
If registration drifts, a vein may miss its embossed groove, and the illusion fails instantly. Some tiles add structured effects.
Textured rollers emboss grain, and printing is aligned so veins follow ridges and knots.
Some lines apply granules for slip resistance, especially for bathroom floors where wet traction matters.
Other lines use micro-textured matte glazes that feel silky but still resist fingerprints.
For high-end looks, factories may apply multiple glaze layers, a base glaze, printed decoration, and a protective top coat.
The top coat can improve scratch resistance or tune the final gloss level.
Between layers, infrared or hot air stations set coatings so they do not smear. The entire glazing line is kept extremely clean.
A single hair, dust clump, or oil droplet can create a crater, a streak, or a fisheye defect after firing.
Operators clean and calibrate print heads. A clogged nozzle can create a missing line across every tile.
Even water quality matters, because dissolved salts can leave marks or change drying behavior.
A glaze that melts too easily may flow beautifully but scratch more easily.
A glaze that is too stiff may resist scratches but show orange peel texture or incomplete leveling.
Matte glazes often rely on microcrystals or controlled surface roughness, which must be tuned carefully.
For glossy tiles, the challenge is avoiding bubbles and pinholes while achieving mirror-like smoothness. Color control is a major part of glazing.
Ink and glaze batches are logged, and color is checked against standards under controlled light.
Digital printers run calibration patterns, so every nozzle delivers the correct drop volume.
When a nozzle clogs, the system may compensate, but persistent faults must be cleaned to avoid repeating defects.
Special effect glazes add complexity. Some glazes contain reactive components that crystallize during cooling, creating stone-like variation. Others use matte top layers that scatter light, hiding smudges but demanding precise firing to avoid patchiness.
For anti-slip tiles, surface texture is engineered so grip increases without turning cleaning into a nightmare. Manufacturers may also add antibacterial or easy clean additives, though performance depends on chemistry and standards testing.
After glazing, the tiles enter the kiln, the most energy-intensive step in the plant.
A modern roller kiln is a long tunnel with zones that change temperature minute by minute.
Tiles ride on rotating rollers, so they move smoothly and stay flat as they heat. In the preheat zone, any remaining moisture is driven off carefully.
Next, organics in the clays burn out, releasing gases that must escape before the glaze seals the surface.
As temperature climb, the body begins sintering. Sintering is when particles bond and pores shrink, turning a
Fluxes soften and partially melt, allowing grains to rearrange and densify. At peak temperature, the glaze melts fully.
The surface tension of molten glaze determines whether it smooths beautifully or pulls back into defects.
Timing matters. Too short and the glaze may not mature. Too long and it may overmelt and run.
Kiln curves are documented like recipes. Operators track belt speed, burner settings, and zone temperatures, then compare results against reference tiles.
If a glaze shows pinholes, they may slow the ramp or extend a soak so gases escape before the glaze seals.
If tiles warp, they may adjust temperature uniformity, roller support, or body particle distribution upstream.
Cooling is not just turning off heat. It is managing thermal gradients so glaze and body contract together. If cooling is too fast, the glaze can craze, or the tile can crack from thermal shock.
Kiln control uses thermocouples, airflow tuning, and firing curves validated by production samples.
Many kilns recover waste heat to preheat combustion air or warm dryers, improving energy efficiency. When tiles leave the kiln, they are hard, resonant, and permanent. Every defect formed earlier is now locked into the ceramic.
Residence time in the kiln is carefully matched to tile thickness and glaze type.
Thicker tiles need more time for heat to penetrate evenly, while thin tiles heat quickly but can warp if support is uneven. Kiln rollers must stay straight and clean. Buildup can mark the underside and create localized bending.
Plants run control tiles, known reference samples, to verify that the kiln curve is producing the expected gloss and color.
When energy prices rise, plants optimize curves for efficiency, but they cannot compromise defect rates without losing quality.
Defects are the dark side of tile making, and factories obsess over prevention.
Warping can come from uneven pressing density, uneven drying, or uneven heating across the kiln width.
Pinholes appear when gases rise through the glaze during firing, leaving tiny craters. Blisters form when gas pressure lifts the molten glaze into bubbles.
Crawling happens when glaze pulls away, often caused by dust, oil, or an incompatible surface on the glaze cannot wet.
Crazing is a web of micro cracks that can develop if glaze and body shrink at different rates during cooling.
Chipping can come from weak corners, rough handling, or internal stress from uneven cooling. Color variation can come from raw material drift, print calibration drift, or subtle kiln atmosphere changes.
Quality control is not a single inspection at the end. It is a feedback loop through the entire plant.
Any defects have signatures that point back to a specific stage.
A crack that starts at the edge often points to handling damage or uneven drying.
A blister that appears only in dark areas can point to printing solvents or organics burning out too late.
A wave in the surface can point to uneven glaze thickness or roller issues inside the kiln.
This is why factories keep detailed process logs. Defects are diagnosed like engineering failures, not like cosmetic flaws.
After the kiln, some tiles go directly to inspection, while others receive finishing. For certain products, edges are ground and squared in a process called rectification. Diamond wheels trim each side to a precise dimension, enabling narrower grout joints and cleaner lines.
Some surfaces are lightly lapped or satin polished to change feel, but the factory must avoid overheating the glaze.
Finishing lines use water for cooling and dust control, then filter and recycle that water to reduce waste.
Tiles are dried again after finishing, so packaging stays clean and dry.
Rectified edges are measured again after grinding, because diamond tools wear and dimensions can drift. Dust from grinding is captured and filtered, and slurry from wet grinding is treated so solids do not enter wastewater.
Tiles enter inspection lines under controlled lighting. Machine vision compares each tile to reference standards, spotting scratches, specks, pinholes, and printing defects.
Mechanical gauges measure length, width, thickness, and flatness, checking bow, cup, and twist. Because firing shrinkage varies slightly, tiles are sorted into calibers so installers can keep joint lines consistent.
Color is sorted into shade lots so a finished floor does not show patchy shifts from box to box.
Plants perform property tests on samples. Water absorption testing shows how porous the body is and how suitable it is for wet environments.
Breaking strength tests check integrity, while abrasion and stain tests evaluate surface durability. Slip resistance tests may be performed for products intended for wet areas, especially textured finishes.
Tiles that fail can be downgraded or discarded. Unfired scrap is often recycled back into the body mix.
Packaging is also a quality step. Tiles are stacked with face protection, so friction does not scratch the surface in transit.
Boxes are designed to survive humidity and impacts, and pallets are strapped to prevent shifting.
Warehouses store tiles flat and dry because poor storage can create edge damage before the customer opens a box. Then pallets are wrapped, loaded, and shipped to distributors, retailers, and construction sites. Sorting is often automated.
Tiles pass through gates that direct them into stacks by caliber and shade, minimizing human error.
Even within one shade lot, the plant may separate slight tone differences, so high-end customers can specify tighter ranges.
Before shipping, some plants perform drop and vibration tests on packaged boxes to ensure packaging protects corners. Barcode systems track pallets so distributors can reorder the same shade when a project expands.
In a bathroom, installation is where manufacturing meets reality. A flat tile still needs a flat substrate. Dips and hums create lippage where edges stick up. Installers check the floor with straight edges and correct it with leveling compounds when needed. Wet zones often use waterproof membranes, sealed corners, and proper slopes to drains.
Adhesive choice matters. Cement-based thinset is common, but the formulation must match the tile and the substrate.
A notched trowel creates ridges that collapse under pressure, forming continuous contact and avoiding hollow spots. For larger tiles, installers often back-butter the tile to improve coverage and reduce voids. Leveling clips and spacers keep lines straight, especially with larger tiles that show misalignment easily.
Movement joints matter too. Buildings expand and contract, and rigid tile needs planned relief points.
Epoxy grout resists stains and chemicals, but it requires careful timing and cleanup.
Cement grout is easier to use, but it can stain if not sealed and maintained.
Edges and transitions may use trims so corners do not chip and water cannot seep underneath. After installation, maintenance keeps the surface looking new. Neutral cleaners preserve grout and glaze, while harsh acids can damage certain finishes.
In bathrooms, good ventilation reduces mold growth in joints and keeps surfaces safer. A well-made tile can last decades, but only if it is installed with the same care used to manufacture it. Cutting and edge finishing are part of installation, especially in bathrooms with many corners and fixtures.
Wet saws and score and snap cutters produce different edges, and installers choose based on tile type and thickness.
At transitions, installers leave expansion gaps and cover them with trims or flexible sealants.
In showers and wet rooms, grout alone is not waterproof. Waterproofing must be behind the tile.
And even on a perfect install, grout is a maintenance surface. Routine cleaning prevents soap scum and mineral buildup that can make floors slippery.
From clay and kaolin to glass and fire, a ceramic tile is geology transformed by precision. The next time you step onto a bathroom floor, remember the quarry, the lab, the press, and the kiln beneath that quiet surface.